All right, next one, we did our electric field lines. So our rule was our electric field lines always point towards negative and always point out from positive. And the way I said that that rule was made is that we imagine like a little positive point, and which way would that positive point go if it was placed in the electrical field. So that was our rule. For a point charge producing an electric field, you can use this formula. Now why? Because the strength depends on the distance, okay? So it has that distance in there. So the strength of the field depends on how close it is to the actual source, okay? And that's why with this one, Q is the source, okay? So in this one, this is our source charge, okay? Now, if you can't remember, think about your gravitational equations, and your gravitational equation that's just like that, the G is the source spring, okay? Now, you need to be able to calculate net electrical field strength at a particular point when multiple charges are present, both linear and 2D problems. So let's do an example of each. We have our linear and our 2D, okay? So say here we have A is positive and B is positive, okay? And let's say there is point P, okay, in the middle, point P, okay? What is the electrical field strength experienced at point P? I should have drawn my B kind of right in line here. Sorry about that. Okay? So, electrical field strength goes out from positive, okay? So here is my E of A, it's coming out from positive. Here is my E of B, coming out, okay? Now, to find my E at, like, point P, okay, E of A is going to the right. So I'm going to say this is positive. So E of A is positive, and I add that to E of B. But E of B is going left, so that's negative. Okay, so when I'm finding my electrical field strength at that point, that's what I do. So just be careful with your directions. Now, for an example for 2D, say we have A is up here, and B is here, and it's positive, and we're looking for point P, okay? So, at point P, my electric field strength is going towards, or into the negative, okay? Not talking about force here, this is our electric field strength. So regardless of what charge P is, or even if we're told a charge of P, the electric field is still going toward the negative, okay? And the electric field coming from B is coming toward P there, okay? So I'll call that E of B, this is E of A. So what I need to do, you guessed it, draw a new triangle. It is right now tip to tail, but I like to redraw things too. So here's my E of A, here is E of B, and you need to redraw, and this is your E net, okay? So that's your magnitude, and then you find your angle at that point. So use trigonometry, your Pythagorean's theorem, okay? A squared plus B squared equals C squared, and trig to find the angle. For a charge experiencing a force due to an existing electric field, use E is equal to Fe over Q. Okay, so remember this Q is the charge experiencing, right? Okay, right? A charge experiencing a force. Okay, so keep that in mind. Questions relating speed and voltage of a charged particle in a uniform, so that means parallel plate. Okay, uniform electric field should be solved using energies. Okay, so you can use this formula where you know that your delta E is energy but not electric field. Okay. And also remember that EV is a unit of energy. So if you're told to put something into EV, think of it almost as joules. And if you're given something in EV, think of it as joules and do your conversion. And think of it as like it's an elementary volt, right? An elementary volt. Well, what's an elementary charge? 1.6 times 10 to the negative 19, okay? All right, so now, parallel plates. This is also called uniform field or uniform electric field, okay? So, if you see either, if you see either one of those as like parallel plates or uniform electric field, they mean the same thing. For those, you never use E is equal to KQ over R squared because this formula talks about the strength is dependent on the distance, okay? With uniform electric field, you assume that the electric field is the same throughout the whole plate. You disregard that it changes a little bit around the outside. Between parallel plates, the electric field is uniform, that's why it's called uniform electric field, but voltage is changing, okay? So your delta V is changing because it's potential voltage. It's the highest between the plates, and then as you get closer and closer, it decreases. The following equations can be used for parallel plates. Your E is equal to delta V over D, E is equal to FE over Q, and delta V equals delta E over Q.